Good afternoon, dear students. Previous class you learned ionization energy, ionic radius, and successive ionization energy. Today we will discuss the topic periodic trends in ionization energy. You already know about ionization energy. It's a minimum amount of energy is required to remove loosely bound electron from the orbital in a gas isolated neutral gaseous atom. Okay, so some variation in the ionization energy in periodic table, period wise, and also in the groups. Ionization energy, it is increasing along the period it is increasing. We have totally 7 periods, so in the periods it is increasing with some exceptions. Okay, we have some exception case with the increasing the ionization energy along the periods. Now we are going to see the ionization energy periodic trends in periods. Move from left to right. Left to right of periods. First period, maybe in first period. Okay, we consider in the first period. So see here, the valence electron is adding in the first period with the same shell it is adding. Okay, we add the electron in the elements in same shell. So the number of electron is present is same with the number of proton in the atom. So the successive increase of nuclear charge is increasing the electrostatic attractive force on the valence electrons. Again, the valence electron, and they require more energy to remove the valence electron and it requires more energy, so it's resulting the higher ionization energy. So increasing the electrostatic attractive force in the valence electron, it's require more energy to remove one electron. This is ionization energy. Take page number 74 in your book and look at that modern periodic table. Periods. First period, generally it is increasing its ionization energy. Look at the second period. In second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. They fill the electron in same orbital. The valence electron is same. 2s, here also 2s. Here 2s, 2p, 2s, 2p. So here filling of electron in the second period is in the same orbit. Okay. But in the ionization energy, the ionization energy have some exception in this group, in this period 2, to calculating the ionization energy. Take page number 85. This is the graph which is given here with atomic number versus ionization energy. Ionization energy, and this is atomic number. Okay. So in the second group, in the first second period, so what are the elements are present in the second period? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Finally, it's neon. Okay. So atomic number is plot against ionization energy in this graph. It is denoted here with the elements which is present in group 2: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. What is the atomic number of lithium? It's 3. Okay. 3, like it is increasing. Okay, 3, 4, 5, 6, 7, 8, 9 and 10. Okay, now take this one from the ionization energy concept. If you move from left to right, generally it may be increase. Okay, it is increase, but in this case we have some deviation. You can see this deviation: beryllium and nitrogen, you have some deviation, and neon also. Okay, they are not in the straight line, but they have some deviation. Why they got some deviation with the plotting of atomic number and the ionization energy in a graph? Because of the electron which is filling in the orbital, in some cases it's completely filled. So the completely filled electrons and half filled electrons are more stable than the other electrons that we already know from the unit 2 electronic configuration. The energy of orbitals, we already know the stability of orbital. So from that we are going to explain the ionization energy of the deviation case in this group 2. From that graph we expected here boron had to be a higher ionization energy. Why? Because boron has higher atomic number than the beryllium, but it doesn't. Why? Because of the filling of electron in same orbital. Lithium, what are the orbital is present in lithium? 1s2 and 2s1. So the final valence electron is 2s. In the beryllium also it is 2s. In lithium you can see only one electron is present. Beryllium, it's contain 2 electrons. So the orbital which is present in beryllium, it's contain 2 electrons, 2s2. Okay. So now filling 2 electrons in one orbital, it is more stable than the incomplete filling of electron in a orbital. Okay, so because of this concept, the stability of the orbitals in the partially filled, fully filled and unsymmetrically filled orbitals in boron and beryllium, it is getting the deviation here because of the stability of orbital. Okay, so boron contain 5 electron, but beryllium contain 4 electron. In boron we have the orbitals are 5 electrons, right? So 1s2, 2s2, then 2p1. Now you can see which one is the valence electron of boron. Valence electron is 2p1, only one electron. In p orbital we have only one electron. Is it a symmetrical one, or it is half filled or fully filled? No. So we have only one electron in 2p orbital. So what it is explaining? So this electron is loosely bound electron. So we require only small amount of energy to remove this electron. Okay, so we need only minimum amount of ionization energy. So the ionization energy of boron is less than the beryllium. Why it is less than the beryllium? Because beryllium contains 2 electron. It is completely filled s electron. So they require more energy than the boron because it's completely filled. It is completely filled. You know the stability of orbital. The unsymmetrical orbital is not a stable one, and symmetrical orbital is stable one. Or you can say the symmetrical orbital or half filled or fully filled orbital. 3 are same. Okay. So half filled, fully filled and symmetrical orbital, these three are same. So this one is a symmetrical orbital. So this beryllium is required more ionization energy to remove a electron from this orbital. Okay. So write the electronic configuration for beryllium: 1s2, 2s2, and boron 1s2, 2s2, 2p1. Here the valence electron is 2s2, so 2 electron. In 2p only one electron is present, it's 2p1. Okay, so this is symmetrical one, this is unsymmetrical one. Which one is more stable? This is stable than this. Okay, this is not stable. So because of the stability of this valence shell, it's required more ionization energy. So the ionization energy of beryllium is 899 kilojoule mole power minus 1, or we can say this one is electron volts. The ionization energy of this is beryllium, and for boron it is 800 kilojoule mole power minus 1. You can compare this two. Which one is more, which one require more energy? This beryllium require more energy and boron require less energy. And we have another case in the same graph, figure 3.2, page number 85. See this one. After beryllium you have carbon, nitrogen, oxygen, fluorine and neon. Carbon, this is 5 and this is 6, 7, 8, 9, 10. Neon, you know that 10 is noble gas and it's more stable than all the elements which is present. Okay, so the noble gases are more stable. So leave that one now and come to this topic: carbon, nitrogen, oxygen and fluorine. Carbon, it's 6, nitrogen 7, oxygen 8. Compare this nitrogen and oxygen. Which one has more atomic number? Oxygen has more atomic number than the nitrogen. It is 7 and oxygen is 8. Fluorine is 9. But you can see the deviation in nitrogen and oxygen. You can see the deviation. This is higher than the oxygen. This nitrogen is higher than the oxygen. As like the same beryllium and boron, it's explaining here the ionization energy is higher in nitrogen and oxygen, is explaining with the stability of orbital with the electronic configuration we explained here. Okay, so we have another exception, that is nitrogen and oxygen. What is the atomic number of nitrogen? Is 7. Oxygen is 8. Write the electronic configuration: 1s2, 2s2, 2p3. 1s2, 2s2 and 2p4. Now write the valence shell in the orbital box wise. You write it. B block B. Okay, so this is 2p3, this is 2p4. Right here, 1 2 3, 2p4. Now fill the electron in it. 1 2 3, because only 3 electrons. Here you fill 1 2 3 and 4. Now compare this two. Which one is symmetrical one and which one is unsymmetrical? This is symmetrical and this is unsymmetrical. Why? Because symmetrical distribution of electron in the orbital, unsymmetrical distribution of electron in the orbital. Compare this first box and second orbital, and first orbital and second orbital, only one electron. And compare this two with this third, 1 electron. So these three are same, but here it's contain 2 electron, 1 electron, 1 electron. So we have some exception in nitrogen and oxygen because of the symmetrical distribution of electron in the orbital. So this is more stable than the oxygen, and they require here because this is more stable. Okay, so more stable means they need more energy. The stable electron is difficult, it's some difficult, or it's require more energy to remove the electrons. Okay, so because of that stability, it's require the nitrogen compound require more ionization energy than the oxygen, because in the fourth electron is a loosely bound electron. This one is loosely bound electron with the orbital, but here both these three are stable one because it is symmetrical distribution. So there is not a symmetrical distribution in oxygen. So this last electron is the loosely bound electron, so we can easily remove that last electron from that oxygen. That's why the deviation is more in, or the ionization energy of nitrogen is more than the oxygen. Okay, it's already given in your graph 3.2. So the ionization energy of nitrogen is 1402 kilojoule mole power minus 1. Ionization energy of oxygen is 1314 kilojoule mole power minus 1. Here it is half filled and here it is unsymmetrical distribution. Because of more stable in the half filled orbitals, it's require higher energy to remove the electron from 2p orbital. But in the oxygen it is not half filled or fully filled. So it's require only minimum energy to remove an electron from this. Next is periodic variation in groups. So ionization energy is decreasing in down a group. So you can consider a group, you can take a group here. How many group we have? Totally 18 group. Look at the first group. It's contain hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Okay. So now here if you are moving from up to down, the ionization energy is decreasing. Why it is decreasing? Because the distance from the nucleus and the valence electron which is present in the outermost shell is increasing. So the distance from nucleus and valence electron is increasing when we move from top to bottom of the group. That's why ionization energy also it is decreasing, because the nuclear charge, the electrostatic attractive force from the nucleus to electron of the valence shell, it is less. So that's why this ionization energy is decreasing from top to bottom of the group, it is decreasing. Okay, so the nuclear force of attraction in the valence electron is decreases with the decreasing the ionization energy. So ionization energy and the shielding effect, we have some relation in the ionization energy and shielding effect. When move from top to bottom, you can see number of orbital is increasing. Number of orbital is increasing and number of electron is present in that particular orbital, that is also increasing. So the inner electron or inner orbital electrons are shielding, or they are covering the electrostatic attractive force of nucleus with the valence electron, that means the outermost electron. So decreasing the effect of nucleus or the attractive force of nucleus, here the ionization energy also it is decreasing. So the inner electron decreasing the attractive force of nucleus is acting on the valence electron. So the ionization energy is also decreases. See this, page number 85, table 3.3 figure. We plot here atomic number in x-axis, ionization energy in y-axis for group 1. Which one is group 1? First alkali metals, S block elements. So first group it consists lithium, sodium, potassium, rubidium, cesium and francium. Now see this one, lithium have more ionization energy. It has more ionization energy than the sodium because it's increasing the atomic number, means number of orbitals is increasing. Number of orbital is increasing. Okay, so number of orbital is increasing. So the electron which is present in the innermost orbitals, they are shielding the attractive force of nucleus to the valence electron. They are screening. Okay, so because of this screening effect or shielding effect, the nuclear attractive force from nucleus to valence electron is decreases. Because of decreasing the valence attractive force of nucleus, it's loosely, the valence electrons are generally they are loosely bound electrons. When look at this one, figure 3.3, you can easily understand lithium, it contains only one orbital. So one has only two orbital, 1s2 and 2s1. So this is the shielding effect of lithium is less than the sodium because atomic number of sodium is 11. So it's contain 3 s orbitals. So the inner electrons in the shell is more than the lithium. Then compare with potassium. Potassium contain 4. It is in the fourth period. So fourth principal quantum number, it's contain more shell than the sodium. So their atomic energy is decreasing with the ionization energy is decreasing with the decreasing screening effect. In the rubidium same case, and cesium also it is same case. So it is decreasing their ionization energy with the increasing atomic number and decreasing their with the depend upon the shielding effect. Fourth periodic trend is electron affinity. Electron affinity. We learn ionization energy. It is a required energy, and here this is released energy. Okay, this is released energy. With there we require more energy to remove the electron. So this is opposite from the ionization energy. Electron affinity is opposite of ionization energy. So for the addition of electron, for adding electron into one atom, it's release some energy. That energy is known as electron affinity. Generally it is expressed by the unit kilojoule mole power minus 1. And the definition of electron affinity is defined at the amount of energy is released. It is defined at the amount of energy is released. Energy is released when an electron is added to the valence cell of the isolated neutral gaseous atom. It is in the ground state to form its anion. So in the electron ionization energy, they form only cation, but in the electron affinity they form only anions. Okay, to form anions. That That means what? Cation means they lost the energy. Anions means the addition of energy. Okay. So now you see this one. Releasing energy with addition of electrons. With addition of electron in neutral isolated gaseous atom in ground state. There also we mention its ground state. So for remembering this too, you remind this is ground state. Both are in ground state. To form anions. So it is expressed by the unit kilojoule mole power minus 1. We took one element. We consider one element is A. It's required. It's released some energy with the addition of one electron. So we add here with the addition. So addition of one electron in one element. What is the product of this equation? Its form or its produce here anions. So A minus is denoting addition of electron. So A minus means one electron is added here. If they are mentioned in a book, if the case they are given A2 minus means, what is the meaning of A2 minus? 2 electron is added in the element A. Okay, so F, for example, F minus. So what is the meaning of F minus? It's accept one electron, or we add one electron in fluorine. So with the one electron, then again add one electron with the fluorine. What is the resultant one? F 2 minus. Why it is 2 minus? Why this first 1 minus is become first 1 anion is become 2 anions? Because one more electron, addition of one more electron. So it's become F2 minus. It's denoting here addition of 2 electron in this. Okay, so the result for this A, adding with one electron, it's release some energy that is known as electron affinity A. There we mention IE. Why? Because ionization I, energy E. Here electron affinity E is denoting electron, A is denoting affinity. So minus is electron, the anion is formed because of the addition of energy. Here also we have some successive energies. If you add more electron into that particular anions, then you will get the successive energy. So you have some variation in the electron affinity in a period. As we move from the alkali metal to halogens in a period. So first period, if you move from left to right of the period, then you can see the electron affinity is increasing. So electron affinity is increasing means the amount of energy released also increasing. Why? Because electron affinity is increasing. That means releasing energy is increasing. So the amount of energy is increasing. When we move along from left to right of the period, the electron affinity is increasing with increasing the amount of energy. This is due to the increase of nuclear charge and decreasing in the size of atom, because nuclear charge is increasing. Why nuclear charge is increasing? Because of the addition of electron into the elements. Okay, so if you add more electron in here, then the proton amount of proton is increasing, so the nuclear charge is increasing, and also the size is decreased. Why its size is decreased? Because the electron is adding in the same shell, so size is decreasing, but the electron affinity and the amount of energy is increasing with the increasing the nuclear charge. Like the ionization energy, we took here beryllium and nitrogen. Is the exception case in group 2. Beryllium is 4 and nitrogen 7. Look at this. Beryllium and nitrogen, they are the exception case in this electron affinity. In the beryllium, we have a electronic configuration is 1s2 2s2. 2s2 is the valence cell, and here we filled 2 electrons, so this is stable one or symmetrical in completely filled orbital. Here it is half filled orbital and symmetrical one. Because of this stability, the addition of extra electron will disturb the stability of these two compounds in second period. Okay, so because of this, we have almost zero affinity for this beryllium and nitrogen. Okay. Look at page number 86 and figure 3.4. See this one. Lithium. Their electron affinity is more, but beryllium, it is nearly zero, and nitrogen also, it's nearly zero. Why it is nearly zero? Because nitrogen and beryllium have this beryllium contain completely filled orbital, nitrogen contain half filled orbital. Because of the stability of beryllium and nitrogen, they if the addition of electron in the beryllium and nitrogen will disturb the stability of beryllium and nitrogen. Because of this electronic configuration stability, the electron affinity of beryllium and nitrogen is almost zero it is almost zero. And the noble gas, we have some special case, because noble gas is completely filled. I already told you it is it's more stable compound than the other elements which is present. So noble gases is required some energy to adding the electrons. Okay, but electron affinity in the neon is in the noble gases, it's not it's unfavorable one. Okay, and the halogen have electronic configuration is ns2 np5, so their electron affinity is always greater. Why? Because they have the general electronic configuration is ns2 np5. So filling np5, then in the orbital of np5 they need only one electron to get the stability. That's why fluorine have the higher it has higher electron affinity than any other element in the particular in a period. Look at this fluorine. What is the atomic number of fluorine? 9. Electronic configuration 1s2, 2s2 and 2p5. Write the box electronic configuration 1s2, 1, 2. Then 2s2, 1, 2. Then what is the next one? 1, 2, 3. 2p5, 1, 2, 3, 4, 5. They have only one vacant place to fill the electrons. So this type of compounds are they has more electron affinity. Because of getting one electron in that particular compound, they will be stable. That's why they require one electron. So the electron affinity of halogens, generally electron affinity of halogens are greater. So today's topic over, students. Just read it out and compare this all the theories, all the facts with the modern periodic table. You can easily understand that one. Thank you, students.